In this next module, we're going to focus on temperature regulation and fluid balance during exercise. During exercise, about 80% of the energy that's dissipated is so as heat, and that needs to be removed so that the body temperature doesn't rise to critical levels. We're going to look at how heat is lost during exercise. There are a number of physical processes that are involved here: the conduction and convection, radiation, and the evaporation of sweat. Conduction and convection really refer to the movement of air or water in the case of swimming, and contact. When athletes are swimming, the temperature of the water can have an impact on heat loss, and that's why so much attention is paid to ensuring that competitive swimming pools have an optimal temperature range to not impede or to facilitate heat loss. However, if we focus primarily on exercise in air, then the airflow over the body will facilitate heat loss, but as the environmental temperature increases, the evaporation of sweat becomes more important. In order to evaporate sweat, the heat from the body must be transferred to the skin, and this involves the cardiovascular system, and increases in skin blood flow deliver the heat to the surface of the body, transporting it away from the contracting muscles. And here is the challenge that the exercising human has to confront, particularly if they're exercising in a hot environment. The competing needs to deliver oxygen to contracting muscle, to deliver heat to the skin, and to ensure that there's maintenance of oxygen delivery to the brain. If we look at the relative contribution of these heat loss mechanisms to exercise with differing ambient temperatures, as you can see, as the ambient temperature increases, the relative proportion of heat loss due to evaporation increases. And we'll talk more about the importance of sweating in a moment. If we look at body temperatures during exercise, and these are often measured either by putting a thermistor into the esophagus, or another part of the gastrointestinal tract, the rectal temperature is often used. Here's the esophageal temperature response to exercise at about 60 to 70% of VO2 max for about an hour. And what you see here is a rapid increase in temperature and then a slower, steady level or slight increase. The reason for this step increase is that the rate of heat production increases quite rapidly at the onset of exercise. The rate of heat loss is somewhat slower. And so there is an error signal, if you like, in the regulation of body temperature. It's not regulated at a different level, it's just that the balance of heat loss and heat production is out of balance early on, resulting in a rise in the core temperature initially, and then it tends to level off. As exercise continues and metabolic heat production is maintained or increased, and the ability to dissipate that heat, the core temperature may drift upwards slightly. And after exercise, when exercise finishes, you can see this rapid drop in body temperature. So the most important determinant of the core temperature during exercise is the rate of metabolic heat production, i.e. how hard the exercise is, or the exercise intensity. If you look at other tissues, here is the increase in muscle temperature, and this is as a percent of the oxygen uptake. And as you can see, as you increase the exercise intensity, you increase the muscle temperature. Here is the rectal temperature and the esophageal temperature, which are relatively close. The rectal temperature is probably, because it's influenced by heat returning from the exercising legs, is slightly higher sometimes than the esophageal temperature. In response to this increase in metabolic heat production, the main mechanism for losing heat is the evaporation of sweat. And here is the sweat response to exercise of about 40 minutes duration at different exercise intensities, here expressed as a percent of VO2 max. And as you see, as the exercise intensity increases, there are increases in the sweating rates. So again, the sweat rate during exercise is directly related to the rate of metabolic heat production. If we look at the composition of sweat relative to other body fluids, and in this table you see the concentrations of 4 key electrolytes and the osmolarity of sweat compared with plasma and the intracellular fluid within muscle. And what you can see here is that sweat is hypotonic. So although with prolonged sweating you may lose significant amounts of electrolyte, the major constituent is fluid. And so that has implications which we'll talk about in a moment. Sodium is another important electrolyte, sodium chloride, can be lost in sweat, and often in individuals who've exercised for some time, the skin tastes salty, and sometimes you can even see salt deposits on the surface of the skin once the water has evaporated. The sodium content of the sweat is influenced by the sweat rate. The higher the sweat rate, the less chance there is for sodium reabsorption. And after a period of training or acclimatization, the sweat sodium content tends to be lower, which helps minimize the sweat loss and preserve the body fluid volumes in the trained state. In terms of the control of sweating during exercise, it is under sympathetic control, and the sympathetic cholinergic nerves have an important role in activating the sweating process, in modifying the skin blood flow. The core temperature is a major driver of the sweat rate, and this, as I said earlier, is driven by the rate of metabolic heat production or the exercise intensity. The skin temperature can also influence the sweating rate. Cooling the skin will tend to reduce sweating. Warming up the skin will tend to increase sweating. But the relative importance of the core and the skin is very much weighted in favour of the core, in the order of about 10 times in terms of the relative signal to sweating. During exercise, there's an increased sweat gland recruitment, but there's also an increase in the sweat released per gland. And dehydration, the loss of body fluid, and the associated plasma hyperosmolarity and hypovolemia reduce sweat rate and sensitivity and increase the sweating threshold. The consequence of sweating is that you lose body fluids. And we'll talk about this in the lecture after next, but there are physiological consequences. There is a slightly higher body temperature when you become progressively dehydrated, and you can see from this table that the core temperature here in the latter parts of exercise was higher than in the control trial when subjects' fluid losses were compensated for. This was associated with a slightly lower stroke volume and a slightly higher cardiac heart rate. You can see here then that over time the progressive loss of fluid from the body, including from the plasma space, is associated with a reduction in cardiac output. And you can see here a slight reduction in two-legged blood flow. And it's really the combination of hypothermia and dehydration during prolonged exercise that begins to challenge the muscle blood flow. The mean arterial pressure, you can see, drops slightly towards the latter stages of this type of exercise, and the forearm blood flow, which is often used as a proxy for the cutaneous blood flow, will also drop off. And so the loss of fluid, although it's important for dissipating heat, has challenges to the cardiovascular system. In terms of body core temperature as a determinant of exercise performance, there have been a number of studies that have correlated the core temperature during exercise with the ability to continue that exercise for some time. And you can see in this study that either preheating or pre-cooling impacted upon exercise tolerance. And so the rise in body core temperature and the associated cardiovascular consequences is associated with fatigue during prolonged strenuous exercise. If you superimpose environmental temperature on that exercise-induced heat production, then that's an additional challenge for the exercising athlete. And as you can see here, if you go from a normal temperature at about 20 degrees and you go to a hot environment at 40 degrees, a marked reduction in exercise tolerance. And we'll talk more about that in the next lecture. However, interestingly, if you move from 20 degrees to 3 degrees, you can actually see an increase in exercise tolerance. And this suggests that even the thermal load associated with exercise at 20 degrees can impact on exercise performance, such that moving to a cooler environment and thereby facilitating the removal of heat by the various processes that we've talked about can improve exercise performance. I should also add that an important determinant of sweating is the environmental humidity, and often an increase in humidity has more profound effects on exercise tolerance than an increase in temperature under dry conditions, because it's only when the sweat is evaporated that you truly derive the benefit of that heat loss. If the sweat drips off, you have none of the benefits of losing heat and all of the disadvantages of losing that fluid. In the next lecture, we'll look at how exercise in the heat can impact on performance.